everyone, today we are going to start the very last chapter of semester 1, and that chapter is going to be talking about exponential growth and decay models as well as logarithmic functions. Before we get started with this lesson, I would like you to please go ahead and complete this really quick warm-up. I want you to evaluate the expressions without a calculator. We have for letter A, 5 to the negative second power. For letter B, 8 to the 2/3 power, and for letter C, that's negative 3 times 4 to the 3/2 power. Please pause the video and try these problems on your own, and when you have an answer, please restart the video and we'll see how well you did. All right, for the first one, we have ourselves a number that has a negative exponent, which means that it's not happy where it's located. So I'm going to rewrite this problem as 1 over 5 to the positive second power, which is 1 over 25. For the next one, letter B, what I would recommend that you do is rewrite the base using exponents. So we know that 8 is equal to 2 to the 3rd power, so I'm going to write that as 2 to the 3rd power to the 2/3 power. I'm going to multiply my exponents. And what we find is that the 3's will cancel out, and I'm left with 2 squared, and 2 squared is 4. So our answer is 4. And then next, I'm going to leave that negative 3 in front, and I'm going to work with the 4 to the 3/2 power. I know that 4 is really 2 squared, so I'm going to rewrite the base of 4 as 2 squared, and I'm going to raise that to the 3/2 power. So that means that the 2's will cancel out, and I now have negative 3 times 2 to the 3rd power. So 2 to the 3rd power I know is 8, so this is negative 3 times 8, and negative 3 times 8 is negative 24. So our answer is negative 24. Hopefully these expressions are easy for you, and if they are not, please make sure that you have a conversation with me. This concept will be on your final exam, and I want to make sure that you feel comfortable with it. So our learning targets for today, our goals, should I say, is I want you to be able to say, I can graph an exponential growth model or growth function using a parent function reflection stretch shrink translation table. And I can use exponential growth models to make predictions about real world occurrences. And I can find the ending balances of accounts given an interest rate and how often the interest is compounded. So we're going to be working with a lot of story problems, a lot of application of exponential functions in this lesson. So some quick vocabulary that you're going to see very often in this unit, and that is an exponential function. An exponential function is in the form of y equals a times b to the x power, and that's where a cannot equal 0. So that's important that the number in front is not allowed to equal 0, otherwise we don't have ourselves an exponential function. And the base is our b value, it's the part that has an exponent, is a positive number other than the number 1. So it's a positive number, which means b is greater than 0, and b cannot equal the number 1. If it did equal the number 1, then we would no longer have an exponential function. Now, an exponential growth function is a function that's written in the form of y is equal to a times b to the x power. But a is greater than 0 and b is greater than 1. So a is a positive number and b is bigger than the number 1. So you're going to see a bigger number, like the number 2, the number 3, the number 4. And you're going to see a positive a value. So that a value is going to, we always typically want to have an a value that is positive for exponential growth functions. So both of these conditions need to be satisfied in order for you to have an exponential growth model. A growth factor is your b value. So when you have the function in the form of y is equal to a times b to the x, that b value is called your growth factor. It's how quickly the graph is increasing. So your growth factor is always going to be b, and we call that your multiplier sometimes. What are you multiplying by each time in order for you to get the next number? And the next vocabulary word is asymptote. And we haven't really talked about that this year very much, if any. And what an asymptote is, it's a line that we're going to draw as a dashed line. So all of our graphs will have a dashed line that represents an asymptote. It is a line that the graph approaches more and more closely. It will never cross that line. So our graph never crosses the asymptote. So please make sure that your graph never crosses the asymptote. For exponential functions, it's going to be a horizontal asymptote, and for logarithmic functions, it'll be a vertical asymptote. But for exponential models, it's going to be a horizontal line. Horizontal lines are y equals a number equation, and we're going to talk about what that number is in just a second. So for exponential functions, it's going to be a horizontal line. For logarithmic functions, it'll be a vertical line. Logarithmic functions, we'll start talking about those in section 7.4. So let's go ahead and talk about exponential growth functions. Hopefully you've seen these before in Algebra 1, and this is just a nice refresher of this function. It says the function y is equal to b to the x is called the parent function, assuming that b is greater than 1. So we don't necessarily have a number that we would say is our parent function. We just say that b is greater than 1 and y equals b to the x is our parent function. It is for the family of functions of growth functions with a base of b. The general shape is what you see here. It's going to look like a sideways J that's going to be increasing very, very quickly and approaching a line. The line that it's going to be approaching is our asymptote, and in this case, our asymptote is located at y equals 0. That is our asymptote. The graph rises from left to right, passing through the points 0, 1, and 1b. These points are important because these points are your parent function, and they will change based on what your b value is. So when you're creating a table of values, because we're going to be creating a parent function, reflection, stretch, shrink, translation table, just like we've done in the past, the nice thing is that you only have 2 ordered pairs to know. You only need to know 0, 1, and 1b. So these are the only points you need to know. Please make sure that you have these ordered pairs memorized, that you recognize it, that it goes 0, 1, and 1b. For every single one of these problems, you will also be required to identify the domain, the range, and the asymptote. What's really cool is that we have an arrow pointing from left to right, so that means that our domain is going to be all real numbers, but our range is going to be different. Since we have our graph approaching a line, approaching our asymptote, the range is going to be restricted. And in this case, for our parent function, our range is going to be all values of y greater than 0. And that 0 comes from our k value. And we're going to talk about what our k value is in just a second. Notice that there's not an equal to for your range. And that's because our graph will approach a certain number, but it won't ever cross your asymptote. Your asymptote is going to be y equals 0. Your asymptote is horizontal. Think of a hoy. Horizontal line, 0 is the slope, y equals a number. And these two numbers should be exactly the same. And once again, they come from our k value. So the graph of y is equal to a times b to the x power can also be translated. So we still have y equals a times b to the x minus h plus k power, or plus k. And that is where the h and the k and the a value all have the exact same properties of what we've already studied this year. So our a value represents our vertical stretch or our vertical shrink. That means that we're going to be multiplying all of our, when we do stretch or shrink, we'll be multiplying all of our y values by the absolute value of a. So that is in the S column. We're going to multiply all y values by the absolute value of a. Now, please note that for y is equal to a times b to the x, notice that your h value and your k value are 0. The y-intercept occurs at 0a instead of 0, 1. So please just know that your y-intercept will be at 0a. This only works if your h and k value is 0. So only works if your hk value is 0, 0. And you'll notice that. You'll see that you're not adding anything in the exponent position, and you won't be adding or subtracting anything outside of the exponent position. Then you'll see that we'll be translating the graph horizontally, h units, and vertically, k units, where once again, h is the opposite of what you see, and k is exactly what you see. And then your translation vector is hk. And hk, the k value is going to be the most important part. The k value helps you to determine your range and asymptote. So that's what I want you guys to write down. The k value helps you to find the range and horizontal asymptote. Once again, if you notice that your a value is negative, I forgot to write that down, then you're going to have a reflection across the x-axis, which means that you'll multiply all of your y values by -1 in your r column. And then we have our r column, our s column, and then our hk comes from our t column. So both of those are translation. All right, let's go ahead and move on. Going to graph 3 different functions by making a parent function, reflection, stretch, shrink, translation table. So we're going to make the table, we're going to sketch the final graph, and then we're going to identify the domain, range, and asymptote. So on your homework, please make sure that you have all of that information for every single graph that you are assigned. So we're going to graph y is equal to 1/4 times 6 to the x power. For all of these problems, I strongly recommend that you identify the following things. The first thing I want you to identify is the parent function. The parent function comes from, remember that your parent function is y equals b to the x power. So in this case, our b value is 6. So our parent function is y equals 6 to the x power. I also recommend that you identify your a value. In this case, it's 1/4. Our b value is 6. Our h value, we're not adding anything in the exponent, so that's 0. And then our k value is also 0 because we're not adding anything on the outside. So always identify that information first. Next, we want to come up with our table of values. So I'm going to create my parent function table, which what's really nice about that is it's always 0, 1, and then 1, comma, your b value. And our b value in this case is 6. So 1, 6 is my parent function. In this case, I do not have an a value that is negative, so I do not have a reflection, so I'm going to write none. Stretch shrink, that comes from multiplying all of your y values by your a value, by the absolute value of a, so I'm going to multiply everything by 1/4. So I have 0, 1/4, and 1, comma, 6/4, that's equal to 3/2, and 3/2 is 1.5. If you want to write that as 1, comma, 1.5, that's fine. It might be even easier to graph. We don't have a translation in this case since we're not adding anything, so I'm going to write none. So my last set of ordered pairs, this is what I'm going to plot. So before I do that, though, I would strongly recommend that you identify your domain. Domain is going to be all real numbers. Your range will come from your asymptote. Your asymptote in this case is going to come from your k value. So your asymptote, that's going to be y equals 0. So that means that our range is going to be all values of y greater than 0. And the reason why it's greater than is because we did not have a reflection across the x-axis. So I'm going to create an asymptote at y equals 0. So every single graph needs to make sure that it has an asymptote, a line that the graph is approaching. And I'm going to plot 0, 1/4, and I'm going to approximate where that's located, and 1, 1.5, so that's about right here. My graph is going to look like a smooth J, like a curve that is increasing, and that is our graph. That's all that you have to do. So let's go ahead and look at letter B. For letter B, the first thing I'm going to do is identify the parent function. The parent function in this case is y is equal to, my base is 3, so that's going to be y equals 3 to the x power. My a value is equal to 2, my b value is equal to 3, my h value is equal to the opposite of what I see in the exponent position, and the opposite of a -2 is a +2, and k is equal to -2. It's exactly what I see that I'm adding or subtracting. So now the second thing I'm going to do is create a table. So here's my parent function, reflection, stretch shrink, translation. My parent function is going to be 0, 1, and then 1 comma my b value, and my b value is 3. So I have 1, 3 as a part of my parent function. Reflection, in this case, my a value is not negative, so I'm going to write none. Stretch shrink, I'm going to take all of my y values and multiply it by my a value. So I'm going to take y and multiply it by 2. So I have 0, 2, and 1, 6. Translation, that means I'm going to take all of my x values and add 2 to them, and take all of my y values and subtract 2. So I'm going to have 2, 0, and 1 plus 2 is 3, 4. These are the ordered pairs that I'm going to plot. But before I plot them, I would recommend strongly identifying your domain, being all real numbers. Your range, in this case, we don't have a reflection, so our range is going to be y values greater than my k value. My k value is -2, and my asymptote is going to be at y equals -2. So I'm going to plot my asymptote first at y equals -2. It's going to be a horizontal dashed line. And I'm going to plot 2, 0, and 3, 4. And I'm going to have my graph approach the asymptote and go through all of the points, creating like this smooth J look to it. And that is our answer. Finally, for letter C, the first thing I'm going to do is identify the parent function. That's going to be located at y equals 2 to the x power. And then I'm going to identify my a value being -1. My b value is 2. I'm not adding or subtracting anything, so I'm going to have h is 0 and k is 0. Now I'm going to create a table of values. Here's my parent function, reflection, stretch shrink, translation. My parent function is going to be 0, 1, 1 comma b. My b value in this case is 2, so 1, 2. My reflection comes from my a value. In this case, my a value is negative, so I'm going to multiply all y values by -1. So I have 0, -1, and 1, -2. The absolute value of -1 equals 1. So because it equals 1, I have no stretch. Then translation, both of them are zeros, so I have no translation. So I'm just going to plot my last set of ordered pairs. But before I do that, I'm going to identify my domain as all real numbers. I have an arrow pointing to the left and an arrow pointing to the right. My range is going to come from the fact that we have a reflection, which means that my graph is going to be below the x-axis, so I'm going to have y is less than my k value, which is 0. And then my asymptote is going to be located at y equals k, and that's y equals 0. So at y equals 0, I'm going to draw a horizontal line, and I'm going to plot 0, -1, and 1, -2. My graph is going to approach the x-axis, and then it's going to continue to decrease. And that is my graph. All right, so the first part of this lesson was all about graphing. The second part of this lesson is all about applying exponential growth models to real-world examples. And one exponential growth model comes from where we are taking something and multiplying it using a multiplier so that it ends up getting bigger and bigger and bigger. Like something that might grow might be cells, or if you end up with like a litter of rabbits, they end up getting bigger and bigger and bigger. So things like that might be something that you'll see with an exponential growth model. So when a real life quantity increases by a fixed percent, each year or some other timetable or some other time period, the amount y of the quantity after t years can be modeled by the equation y equals a times 1 plus r to the t power. So this equation can be used for anything except for interest problems. So any type of story problem will be working with this equation that you will need to make sure that you know or study. So I'm going to write down that this is an anything, we'll use this for anything except interest problems. And we'll talk about interest in just a second. Please make sure that you know this formula. So what A represents is your initial amount or your starting point. R represents your percent increase that we always write as a decimal. Please note that 1 plus R is your growth factor. This is something that you will be asked on your homework. Please make sure that you know how to identify what your growth factor is. What are you, how is it growing each time? Your percent increase is simply R. So if you needed to find a percent increase, you would simply subtract 1 to find what R is. But we always represent those percentages as decimals. And finally, T, most of the time is going to be the number of years. And that's what you're going to see in a lot of problems. The number of years is going to be equal to T. So for example, in example 2, it says in the last 12 years, an initial population of 38 buffalo in a state park grew about 7% per year. Write an exponential growth model giving the number n of buffalo after t years and about how many buffalo were in the park after 7 years. Okay, so our model, the way that we're going to write our model, it might be in our best interest to identify our variables first. So the first thing I'm going to do is identify what my A value is. How much did I start with? And I started with 38 buffalo. So my A value is 38. How much did it grow by? 7%. So R is equal to 0.07. Please be careful whenever you're writing numbers as percentages. A lot of times kids will write that as 0.7, but that actually means 70%. So just be careful. So if R is equal to 0.07, our growth factor is going to be 1.07. And then we're going to write it as T. So my expression is going to be written as, the way that we're going to write this is, excuse me, just lost my train of thought. We're going to write this as y is equal to, or the number of buffalo, we're going to call as n, the number of buffalo, n, is equal to, we started off with 38 times 1 plus r, which is 1 plus 0.07, raised to the t power. So that's n is equal to 38 times 1.07 raised to the t power. That's our model. And now we want to figure out how many buffalo were in the park after 7 years. So that means that we're going to let t equal 7. So I'm going to write n is equal to 38 times 1.07 to the 7th power. And all you have to do is put that into your calculator exactly as you see it. And when you do that, you find that n is equal to about 61. So since we're talking about full buffalo, we just want to round up to the nearest whole number that makes sense. So about 61 buffalo. So now what we want to do is we want to graph our model. And after we graph our model, we're going to use the graph to estimate the year when there were about 53 buffalo. So if I were to graph this, I would say, well, we started with, at year 0, we'll say, we started at 38. So I'm going to plot 0, 38. And that's about right here. And then we have the ordered pair, well, we have 7, 61 that we can graph as well. So I'll graph 7, 61. And I'm going to just connect these 2 points. And have an arrow going through. So looking like it's an increasing J. If I were to regraph this, there we go. And now we want to estimate when there was about 53 buffalo. So 53 buffalo would be somewhere in the middle. It looks like that would be right around 5, 6 years. So somewhere in between here, 5, 6 years. So we can figure out which one makes the most sense by plugging in those numbers. So what I'm going to do is I'm going to let t equal 5, and then I'm going to let t equal 6. So right in there is where 53 buffalo is going to be located. So I'm going to say n is equal to 38 times 1.07, and I'm going to raise it to the 5th power. And when I do that, I end up getting about 53 buffalo, 53.3 buffalo. So I'm going to say that I don't need to check 6 because 53 is pretty close to 53. So I'm going to say after about 5 years. And that's how you're going to solve a lot of these problems. You're just going to guess and check your answer. All right, I'm going to go ahead and move on and talk about one more topic, and that is compound interest. So compound interest is something that can be your friend or it can be your enemy, depending on what your situation is. So if you are investing money into a bank account, if you want interest to be compounded all the time so that you can get as much money as possible. The time when you don't want interest to be compounded is when you owe somebody money. So that would mean that if you owe somebody money and you don't pay them back, you'll have to pay more and more money eventually until you finally pay the entire amount back. So compound interest can be both your friend and it can be your enemy. So compound interest is the interest paid on an initial investment. Notice that word initial. That means a starting investment. And that starting investment is what we call the principal. It is the principal amount. So it's the compound interest is the interest paid on the initial investment called the principal on a previously earned interest. So you might have earned interest on a previous amount and it just keeps compounding. It just keeps adding more and more interest based on the previous amount. So consider an initial principal P, we're going to call principal P, deposited into an account that pays an interest of an annual rate that we call R. And R is always going to be written as a decimal. And it's going to be compounded n times per year. The amount A in the account after T years is given by the equation A is equal to P times 1 plus R divided by N to the NT power. This is a formula that you need to know and use only for interest problems. So please make sure that you study this equation and you're going to use only for interest problems. So we do not use them for any other problems other than interest problems. So you'll need to keep both equations for exponential growth straight, because these are not the only equations that you'll be receiving in this unit. There's going to be one for exponential decay, and there's going to be one for interest that's compounded continuously. So you'll have 4 different formulas that you'll have to keep straight. So far in this lesson, you've learned 2 of them. Please make sure that you learn them, you study them, you know how to use them. Once again, your p-value is equal to your principal. It's your starting amount. Your r value is equal to your interest rate that we always write as a decimal. Your n value is equal to the number of times per year. That interest is compounded, and that's what this entire bolded area represents. And that's if interest is compounded annually. If you see annually, that means that n will equal 1. It's compounded 1 time a year. If you see semi-annually, that means that n will equal 2, because interest is compounded twice a year. If you see quarterly, let n equal 4. Or if you see monthly, let n equal 12. If you see daily, we're going to assume that this is not a leap year, and we're going to always go with 365 days. Let n equals 365. Then finally, t is equal to the number of years that interest is being compounded. The number of years that this is taking place. So let's go ahead and look at example number 3. For example number 3, it says you deposit $2,900 in an account that pays 3.5% annual interest. Find the balance after 1 year if the interest is compounded monthly and annually. So what I'm going to recommend that you do is identify your variables. Our initial amount is $2,900. So we're putting $2,900 into an account. Then our rate is equal to 3.5%, and I'm going to write that as 0.035. N is going to change. For letter A, we have monthly, so N is going to equal 12. And then T, how much time is it taking place? Well, it's going to take place over a year. So I'm going to find my final amount, that's going to be A, is equal to 2,900 times 1 plus my R value is 0.035 divided by 12, and this is going to be raised to the 12 times 1 power. What's really cool about these types of problems is that you can put them into your calculator exactly as you see them, because it's all numbers. Just be careful with how you enter it into your calculator. So I'm literally going to write 2,900 times 1 plus, and then this is a fraction. So any fractions I'm going to insert using parentheses. 0.035 divided by 12, closing my parentheses. And then I'm going to close my parentheses again because now I'm done with this full bracket right here, or this full parenthesis. And I'm going to raise this to the 12 times 1 power, which is 12. And I'm going to press enter and end up with 3,003. So this is going to be, A is equal to $3,003.14. So that's how much is in the account after a year. Let's go ahead and look at compounded annually. So all of our information is going to be the same. P will equal 2,900. R is going to be equal to 0.035. This time, N is going to be annually. So N is going to equal 1, and T will equal 1. So I'm going to write A is equal to 2,900 times 1 plus 0.035 divided by 1 raised to the 1 times 1 power. So this is going to be a little bit easier to enter it into our calculator. I'm going to write 2,900 times 1 plus, and anything divided by 1 is just itself. So I'm going to write 0.035, and then anything raised to the first power is just itself. So I'm going to press enter, and that answer is $3,001.50. So always make sure that you write your answer in terms of money in a way that makes sense. So don't write that as 0.5. Write that as 0.50 because that represents 50 cents. We're talking about money, so we want it to look like money. So example number 4. It says you deposit $5,000 into an account that pays 3.72% annual interest. Find the balance after 3 years if the interest is compounded quarterly. So we deposit $5,000 into an account, so that's our principal. My R value is my rate, so that's going to be 0.0372. My balance after 3 years, so that means T is going to equal 3, and it's compounded quarterly, so N is going to equal 4. And we want to find the balance, which is always our A value. So A is going to be equal to 5,000 times 1 plus R, which is 0.0372, divided by N, which is 4, raised to the N times T power. So that's 4 times 3 power. And I can put that into my calculator exactly as I see it. Maybe clean it up a little bit if you want. So I'm going to write 5,000 times 1 plus parentheses 0.0372 divided by 4. Close the parenthesis, then close the parenthesis again. And I'm going to raise this. If you want to write 4 times 3, that's fine, but I know that 4 times 3 is 12. I'm going to press enter, and I end up with $5,587.45. So that is $5,587.45. And that is our final amount. Our last example of this lesson, it says how much money must be deposited now in an account paying 8% annual interest, compounded quarterly, to have a balance of $1,000 after 10 years. So how much must be deposited means that we want to find our principal. What did we start with? In this case, our ending amount is going to be $1,000. So P is what we don't know. What I do know is that my rate is 8%, and I would write that as 0.08. I know that interest is being compounded quarterly, so that means that N will equal 4. My ending balance is $1,000, so A is 1,000, and it's taking place over 10 years, so T is equal to 10. So I'm going to write 1,000 is equal to P times 1 plus R, which is 0.08, divided by 4, raised to the NT power. So that is 4 times 10 power. So what I'm going to do is I'm going to identify what this number is, and I'm going to put it next door to P. So that's going to be 1,000 is equal to P times. So I'm going to put into my calculator 1 plus, parentheses, 1 plus 0.08, parentheses, forgot about the parentheses, 0.08 divided by 4, close the parenthesis, raised to, 4 times 10 is 40, and I have my number, and I'm going to write that as 2.208, just so that I have enough decimal places. So P times 2.208. At this step, I need to get rid of multiplication, so I'm going to divide both sides by 2.208. And when I do that, I have 1,000 divided by 2.208 is equal to $452.90. Now, when it comes to rounding, I know that a lot of people have different approaches for solving some of these problems. As long as your answer is pretty close to what the actual answer is supposed to be, I will accept it, but it needs to be extremely close to that answer. That is the end of this lesson. I recognize that it was a little bit longer of a lesson, but if you have any questions over anything, please feel free to email me, let me know next time I see you. Otherwise, I hope you guys have a wonderful day.